All right, we are going to do 806 decomposition. You'll notice in the last video, you didn't get to see the clip. That was one I had recorded, in an earlier time, and I just didn't want to re-record it. But for this one, we're going to watch the video clip for the reaction. So for decomposition, we said that decomposition was taking usually an ionic compound, though not always. So we're taking AX. And we're going to keep it nice and simple, and we're going to say that we're always decomposing into our component elements. So this is going to go into A plus X. So we have an ionic compound. We're going to element A and element X. And we're going to have oxidation and reduction again, and we're going to talk about that. The demonstration that we're going to watch is elephant toothpaste. Elephant toothpaste. And it's one example. We're not actually starting with an ionic compound. We're starting with hydrogen peroxide. So on test situations, I tend to not ask about oxidation and reduction when it comes to decomposition, because here I have an ionic compound. Here I have covalent compounds. With covalent compounds, you still have oxidation and reduction, but it can be a little bit trickier. Things it encompasses things we haven't talked about. So I'm going to show you oxidation and reduction for this, but for these two, we're just going to show that we're breaking down into the components. Now, what you're going to see on the video is that there are a lot of other, we're going to take hydrogen peroxide, and we're going to be adding things like dish soap and yeast to that. So you might be thinking, well, that's not decomposition. Well, it turns out that the yeast only provides a surface for this to take place. Nothing else that we're adding to that is causing the decomposition. Hydrogen peroxide is really unstable. It doesn't want to stay together. And so if you provide it with the right surface, it'll just automatically break down. And that's what we have happening. But let's go to the clip, and I'm going to share the audio. I'm going to let this whole clip play. So I'm going to share screen, and I want to share my sound. Share, let's go here. Okay, and it's going to show you different levels. So the first one you see is what we do in class. Let's see, music's still going. Figure out how to stop that. Okay, sorry about that. So you saw that each time they reacted, that reaction got a little bit stronger. Well, why was that? If you noticed, They started off with 10% hydrogen peroxide, and then they went to 20% and then 35%. So there was more of this in the flask and it was more concentrated. Why don't we do that? Well, it's kind of dangerous stuff. It tends to get really unstable and it can spontaneously react. So you have to keep things a little bit safer for the school level. But what we have happening is this breaks down into hydrogen and oxygen. Now I've got something wrong right away. Can you see what it is? Yeah, these guys are diatomic. This was aqueous, so it was dissolved in water. And this was a gas, and this is a gas. Now it's a little more complex. We actually break that down into water, which breaks down into hydrogen, but our end result is we end up with hydrogen gas and oxygen gas. And if you put a splint, a lit splint next to that foam, it'll kind of flare up. Why? Because these guys are flammable and they're in gaseous form. So what we see is as this breaks down, the reason for the dish soap is as the gas blows through that dish soap, it makes bubbles, and that's what makes everything foam. So the yeast was to provide a surface, the dish soap was to be able to see the gas, and the food color was just to make it cool. Now the nice part of this is I'm automatically balanced. I've got H2 and I've got O2, and I started with H2O2, so that was our decomposition. I'm going to skip water because it's basically the same thing. It's just going to be balanced differently. So let's go to mercury 2 oxide. So what I have here is mercury 2 oxide. Pause the video and see if you can figure out what this is going to get broken down into. What's it going to decompose to? All right, hopefully you said mercury and oxygen, but oxygen's diatomic. So we need a 2 there. I've got 2 on this side, but I've only got 1 on this side. So I need to put a 2 here. And now my mercury needs a 2 to balance, and this has an assumed 1. So that's what the reaction is going to look like. Well, because we're starting with an ionic compound here, let's see what the oxidation reduction is going to be. And again, I'm not going to ask you about redox for decomposition. I want to show you how this is going to change. So I start off with mercury, and it's +2. And I start off with oxide, which is -2, because that's my ionic compound, Hg +2, O -2. I'm going to elemental mercury. So here I have a 0. I'm going to elemental oxygen. So that's going to be a 0. If I had a -2 charge here and I went down to 0, that means I lost 2 electrons. To go from -2 to 0, I've got 2 extra electrons hanging around here. That's what gives it the -2 charge. So here I lost electrons. And I had a +2 charge here, and now that's gone. So that means that I gained electrons. And so as it turns out, oil rig, oxidize is lose. Turns out that my oxygen is oxidized and mercury is reduced. And it's just a further reminder that you need to check to see what are your charges when you start and what are your charges when you end. Now, again, I'm not going to ask you, hydrogen peroxide is a covalent compound. It would actually be dihydrogen dioxide if you're going to use it with its typical name. Hydrogen peroxide is its common name. And we're not going to do redox with that. But again, keeping, so our takeaways, decomposition, it's always going to be, sometimes it'll be covalent, sometimes, but we're going to break that down into the elemental components. Again, there's going to be, if you look in your textbook, there's much more complicated decompositions, and we're going to skip those. So that's all we're going to do for decomposition. Thanks for watching.